Hey guys, Miss Michelson here. Today we're moving on to topic 12 in Advanced Algebra 2, which is all about probability. So it might seem like a big jump to go from topic 5 to topic 12, and it kind of is, but the idea is that we want to talk about our main principles of probability before you all take the ACT. And we're going to scroll down to the top of the next page on example number 1. And here we're just going to talk about the general ideas of probability. So it says a box contains 100 balls. 30 of the balls are purple, 10 are orange. If you select one ball at a time at random, what is the probability of each of the following events? So, like normal in our workbook, they kind of jump into some of the more challenging examples right away. So, before we answer part A and part B, we're going to just talk about some more general probability ideas. So, let's start off with the probability of drawing a purple ball. So what is the idea here? Probability, how we're normally going to represent it, is in the form of a fraction. And at the bottom of a fraction is going to be the number of total outcomes or the number of possible outcomes. So in this case, in our scenario, there's 100 balls to pick from. So our sample space or our total is going to be 100. And now on the top of our fraction is going to go how many of our desired outcomes can there be? How many of the balls in the bag are purple? And there's 30 of them. So the probability of drawing a purple ball, we may have been able to do this one on our own, is going to be 30 over 100. We can simplify that fraction to be 3 over 10. So we can say this is our probability. You also may see this written as 30%. So sometimes our probabilities are written in percent forms. But that is just going to be our probability of purple. What else can we answer? Well, if we can do the probability of purple, let's talk about the probability of drawing an orange ball. So again, they're two different events. They don't kind of like rely on each other here. So our sample space or the bottom of our fraction, our total number of outcomes is 100. How many of our balls are orange? 10 of them are. So our fraction or our probability is 10 over 100, which is the same thing as 1/10. Gonna put a box around the answer. I like keeping my probabilities in like a fraction form, but we also could say that 1/10 is 10%. So that is kind of our general level probability, what we want to happen divided by as many possibilities as there is total or possible. But we can kind of raise the bar a little bit like we normally do. If we look at example A, so it says the probability that the ball is either purple or orange. So in this case, we're talking about two different probabilities or two different scenarios that one or the other could be true. So when we're talking about one or the other, we could write this as the probability of P or orange. And if we think about the situation, it's just the idea of reaching in and we're drawing out either a purple or an orange ball. So this probability is going to be equal to the probability of drawing a purple plus the probability of drawing an orange. So just both of those can happen, not at the same time, but they both fall into our category of either or. We already calculated the probability of purple, so this is 3 over 10. We already calculated the probability of orange, that's 1 over 10. So the probability of drawing either or is going to be 4 over 10 or 40%. And then lastly, kind of to spice it up one more time, this part B is asking the probability that the ball is not purple or orange. What do we know about the box? We know that there are 100 balls, 30 are purple, 40 are orange, which means that there are 60 some other color in there. So this probability is going to equal 60 over 100 because there's 100 total, which is 6 over 10. And I put a box around my answer. That's going to be it. Maybe the more technical way that our book would have shown you the answer is when you're finding not the probability of something happening, you're going to take 1 and you're going to subtract the probability that it does come true. So if it's not purple and not orange, it's going to be 1 minus purple or orange. And that's exactly what we found in part A. So that would just be 1 minus 4 over 10 is 6/10. So I posted this page, let me zoom in on here. Right up there at the top is kind of what we just were talking about. The probability of an event occurring is this fraction right here. The number of favorable outcomes, or what you want to happen, divided by the number of total outcomes. Another word for this total outcomes that you might see in some of our further examples is sample space. So those are just all the different possibilities of what could happen. Now we can categorize our different probability events into mutually exclusive versus non-mutually exclusive. So first one, mutually exclusive, items A and B, or probabilities A and B, are going to be mutually exclusive if there are no outcomes in both A and B. So think of A and B as our sample spaces. Our two kind of spaces will be mutually exclusive if they are kind of in their own little bubble. There's no outcomes overlapping. A good example of this is A could be your even numbers, B could be your odd numbers. They are mutually exclusive because there's no overlap. There's no even and odd number at the same time. So when we're given scenarios like this, we have some general formulas that we can use, which these are the ones we used in our very first example on our notes, but we use them kind of intuitively. The probability of A or B is just adding them together. The probability of not A is just 1 minus the probability that it does happen. And then the one we didn't talk about, but the probability of A and B happening at the same time is 0 because it can't exist. They can't happen at the same time. So that is one camp of our probabilities, is mutually exclusive. And then there's another one, another type category that you can fall into, which is non-mutually exclusive. So when we're thinking about our sample spaces or our different outcomes to our problems, we can have part A, we can have sample space B, but they have an overlapping region. So what if we had odd numbers and then prime numbers? There's a little bit of an overlap there because some of our prime numbers are odd. So we have an outcome that's both an A and B. So whenever that happens, we would say these are non-mutually exclusive. And the only thing we need to be careful of there, the only thing that's changing, is when we're finding the probability of A or B, we do what we did in our last one. We talk about A, find the probability of B, add them together, but we have to remember to subtract their overlapping region. So that's when they're kind of like doubled up. You never want to double count something in probability, which happens when we have non-mutually exclusive events. On your Math Excel assignment for today, the first couple of questions are just going to give you a scenario and ask you, are they mutually exclusive or non-mutually exclusive? So we just want to be able to identify those. But that's where we're going to leave off on this page for right now. And we're going to jump back over to example number 2 in our probabilities. And this one is so fun. So this one says, a video game is played on, I said it was fun, is played on a 34 by 20 centimeter rectangular computer screen. And a starship represented by 2 overlapping circles of radius 6 centimeters. Let's draw a picture of what this is going to look like. So I'm going to draw my rectangle. It's a computer screen. It's a 34 by 20 centimeter screen. And what they said is that on the screen there's a starship. And its image is 2 overlapping circles. And they have a radius of 6 and a region of overlap that is 20 centimeters. We're told that a black hole is equally likely to appear at any point on the screen. To the nearest percent, what is the probability that the point will appear within the starship? So if a random dot appears on our screen, we want to figure out what's the probability that it will land in our starship, which is those 2 circles. So let's talk about what our sample space is. What are all of our possibilities Well, it's any point on our computer screen. So, what's the best way, our best measure of every spot on that rectangular computer screen? Well, if we shade it and if we think about what's existing inside that rectangle, we're really talking about the area. And I drew a rectangle there. So to find the area of our rectangle, we know that that's just length times width. Our length here is 20, our width is 34, and I believe that equals 680. Let me double check that real quick before I say the wrong answer, but that is correct. So our area of the entire computer screen is 680, whatever, like, well, it says centimeters, like pixels. And then we want to know the probability. That's like our whole screen. We want to know the probability that the black hole lands on our starship. So let's figure out the area of our circles. This is good practice for our ACT as well. How do we find the area of a circle? What's our equation? It's pi r squared. So what's the only thing we need to know? It's what our radius is. So let's plug that in. Pi times 6 squared, which is 36 pi. But what do we know about these circles? Well, first of all, how many of them are there? There are 2 circles of this size. So let's go ahead and double this. 36 pi times 2 is going to be 72 pi. And I like having pi in my answer because it helps me avoid any decimal, but it doesn't give me a good representation. I don't know what 72 pi is, so I'm going to turn that into a decimal so I have a better idea or understanding of what that number actually is. And I'm going to have to round, but we're okay with that. 72 pi times, let's just make it 3.14, is 226.2. So the area of those 2 circles is 226.2. But we can't forget about our overlapping region. We don't want that area counted twice, because right now it is. So to get an accurate representation of this area, let's subtract their overlapping region, which was 20 centimeters. So let's subtract 20. And we would get the area of our circles, or our starship, is going to be 206.2. Oh no, I ran out of room. 206.2. I'll write it over here. 206.2 centimeters squared. Our whole area is 680. So the last thing we want to do is find their probability. So what 2 numbers do we divide? Well, we take our entire sample space and put it on the bottom. And then we take what we're trying to find, or what we want to happen is we want it to land in the starship. So we divide 206.2 by 680. And it says round to the nearest whole percent. So it's going to be an estimation. So we really should use the squiggly lines there. This is going to be around 30%. So there's a 30% chance that the hole that appears on the screen is going to land on my starship, not anywhere else on my screen. So this is kind of like an area model, which is a little bit funny for our probabilities, but we can still calculate something like that using our ideas of area. And you should expect to see one like that on your Math Excel assignment. We're going to go down to example number 3. Now this is going to introduce a new idea of probability to us. So we're just kind of talk about and interpret these questions. So it says there is 10 cards in a box. 5 of them are black and 5 of them are red. 2 cards are selected from a box at one time. So part A says a card is chosen at random and then is replaced. Another card is chosen. Does the color of the first card affect the possibilities of the second card chosen? So if we draw one, we put it back, and we draw another one, is anything changing about our first and our second event? Are the probabilities or the possibilities changing? And for the first example, I would say no. Why isn't anything changing? Well, we're not changing the number of cards because we put our card back, so there's 10 total cards. And we're not changing the different kind of like outcomes. There's still 5 black cards and there's still 5 red cards to choose from. So nothing's changing about our sample space. And what's the key idea? Nothing's changing because the card is replaced. And when something happens like this, when we have two events that are going on back to back, so we have one thing happens and then the next thing happens, and their probabilities aren't changing, they're not affecting one another, we would classify this as an independent event. So when two things are happening back to back, or it can be 3 or 4 or 5 times in a row, when our probabilities don't affect each other, then we can classify them as independent. But if we look at part B, here it says a card is chosen at random and is not replaced. Another card is chosen. Does the color of the first card chosen affect the probabilities of the second card? So this time, we're not putting the card back in the pile, we're keeping it out. So how is that going to affect my probability? Well, first of all, it affects the sample space. So I originally had 10 cards and I draw one. So my second round, there's only 9 cards left. So I've affected my sample space and I've affected the number of black versus red cards that there are. There could potentially only be 4 black cards or 4 red cards this time, and that's going to affect the probability. So does the first event affect the second event? Our answer would be yes, because the card isn't replaced. So that's kind of like the key thing that's going on here. We're not replacing something, so it's definitely changing. And what would we name this? How could we classify this event? We're going to classify it as dependent. So one event is dependent on the next one. And I've summarized that on our probability sheet here as well. I like to have good concrete examples and definitions. So here we kind of have it written out in words. Our independent events, or A and B, are going to be independent if the occurrence of one does not affect the probability of another. So a good example of this is flipping a coin heads or tails. Every time you flip it, the probabilities are not changing. It's still a 50-50 shot no matter what. And the big idea is when you have two independent events and you want to find the probability of the first event and then the probability of the second event, so probability of A and B happening like back to back, you just take their probabilities and you multiply them together. That's going to be kind of like our formula. But when we have independent events, or not independent, dependent, the probability of one does affect the other one. So our example here was drawing a card from a deck and then you don't replace it. Then you draw another card, so everything's kind of shifting around. And we're going to talk a little bit more about those types of probabilities in our next class. But right now we're just focusing on our independent events and being able to calculate those probabilities. So again, we can kind of understand these ideas, but the best way we're going to get practice with them is by doing an example. And I really like example number 4. I think it's a good one. So we want to find probabilities of independent events. We spin the spinner 2 times. First of all, we know it's independent because the first spin is not going to affect the outcome of the second spin. The probability that we spin in the blue region is 1/3, and the probability that we spin in the orange region is 2/3. So what we're trying to find, or what we're asked to find, is the probability of getting the same color both times. So we're trying to find the probability of the same. So let's talk about how many different ways that could occur. Well, the first one could be spinning and getting 2 blues. So we get a blue and a blue. And the second way could be by spinning and getting an orange and an orange. So we want to figure out what the probability of 2 blues is going to be, and then what the probability of 2 oranges is going to be. And if we're ever stuck in a probability problem and we don't know where to go from here, we kind of interpreted the problem but don't know how to quite get to the answer, one thing we can always do is draw a tree diagram. So when we have multiple events like we do here, we have 2 things going on, a tree diagram is always going to help us figure out what these different probabilities are going to be. And I'm going to start with drawing a point here. This is my starting point. And I ask myself at the start, how many possibilities do I have? So one possibility is to draw or to spin a blue or a B. And my other possibility is to spin an orange or an O. And then we are spinning the wheel one more time. So if we spin blue the first time, our next set of options are again to spin a blue or an orange. And then we could spin a blue or an orange here. So because we're only spinning the spinner 2 times, we have 4 different kind of like pathways on our tree diagram that we can follow. The more spins we add, the more kind of layers to this diagram that we can add off branching here, kind of like if we were to flip a coin heads or tails. So let's figure out the probability, or how do these probabilities tie in here. When we go down the different branches on our diagram, I always like to label what their probabilities are. So the probability of spinning a blue first is 1/3. So I'm going to label kind of that branch or that line 1/3. The probability of spinning a blue here is also 1/3. The probability is not changing, they're not being affected, so it's always 1/3. And the probability of spinning a blue here is 1/3 as well. Let's label our oranges. The probability of spinning our oranges is 2/3 here, 2/3 here, and 2/3 here. If we were to fill out the same diagram but for flipping heads and tails, we know our probabilities are each 1/2. So we have a 50% chance on each of those branches. And what this is going to do is going to help us calculate this probability right here. What's the probability of spinning 2 blues? Well, let's highlight that pathway. So here is our first blue spin, and here is our second blue spin. So out of our 4 total pathways, only one of them has us getting blue twice. How can we calculate those probabilities? Well, the first probability would be 1/3, and the second probability is 1/3. Just like we talked about on our last page, or on our on those independent events, the probability of spinning blue and blue, we multiply those guys together. So this probability is 1/9. So we have a 1 in 9 chance of spinning 2 blues in a row. So I'm going to write that down here. Now let's find the probability of spinning an orange and an orange. So we would have to go down this pathway here, first orange, and then our second orange. This one's really similar, except for our probabilities are different, but spinning O and O is the same thing as taking their probabilities and multiplying them together. 2/3 times 2/3 is 4/9. So this probability, or this branch, has a 4 in 9 chance of happening. Now we had 2 other kind of pathways that we can go down, but they don't have the same, they're not the same color each time. So the first one is blue and then orange, and then the other one is orange and then blue. We could calculate their possibilities or probabilities just by multiplying 1/3 and 2/3. So we would get 2/9 here for this pathway, and then 2/9 here for this pathway. And our problem didn't ask us to find it, but I did want to point out one big idea when it comes to probability. When we take a look at the probability of each pathway happening, so our 4 different pathways, when we add them all together, it should always equal 1. But we didn't necessarily answer this question yet. We found the probability of 2 blues, and we found the probability of 2 oranges, but we wanted to find the probability of getting both colors at the same time. So what that really is asking is the probability of blue, blue, or the probability of orange, orange. 1/9 plus 4/9 equals a total of 5/9. So we have a 5 in 9 chance of going down either that blue pathway or the orange pathway. And that's going to be our final example for today's note.